This is lecture 16. In last lecture, we have discussed that second order time response. So in this lecture, we will be discussing first, if we introduce a pole and a zero to the second order transfer function, then what would be the time response? So that is second order system. So first we consider one second order transfer function in normalized form, and in last class we have discussed why it is called in normalized form. So that is twice zeta omega n s plus omega n square. So the time response of a second order system is characterized by the zeta and omega n. So that thing we have discussed. So now today we will see that if we introduce a pole to this particular transfer function, then what would be the response? So adding a pole to this particular transfer function, then what would be the time response? So if we add a pole to this particular transfer function, so then it would be, suppose the pole is at minus p. It is a real pole, and we have the transfer function twice zeta omega n s plus omega n square. Now to make this particular transfer function normalize, so we need to multiply with a scalar p, because you can see here at steady state the final value would be p omega n square by p omega n square. That means it is equal to 1. So if we apply a step input, that output steady state response is 1. So it is now in normalized form. Now our objective is to see how the time response will be changing whenever we introduce a pole. The reason is, if there is no pole, if this particular term is not there, then we have a second order transfer function, and that response would be completely characterized by this zeta and omega n. But once we introduce this pole, so this is no longer a second order system, and we cannot characterize that response using only zeta and omega n. So if we write the response for this particular transfer function, that is that step response, that qualitative response would be like that. The expression is AUT, the UT is that step input, and then we'll be having that zeta omega nt, B of cos omega dt plus C of sin omega dt plus there is a term that is e to the power minus pt, and here a, b, c, d, these four are constants, and we have seen it in Laplace transform that how to find those coefficients. So here we are not going to find those coefficients, because our interest is to see, that means this particular term actually would affect the time response, and that term is appearing due to this particular extra pole that we have introduced to the second order system. And here it is clear that if P, say if P is sufficiently large, so if P is sufficiently large, then e to the power minus pt, say suppose P is equal to 100. So then this particular term would be dying out very quickly. That means the effect of that pole on the time response would be negligible. And if we keep on increasing that value, that P, that means the pole of that system, that newly introduced pole of the transfer function, if it is moved along the left direction, that means if it is placed far away from that origin, or in other way we can say that if P is large, then the effect of this particular pole would be negligible. So that means in that case we can say that the time response of the second order systems remains as it is. As it is means there would be a little bit difference, but we can neglect that difference. So if P is sufficiently large, the response can be characterized by zeta and omega n. So here what we have seen, that means we have that second order transfer function in normalized form, and when we introduce a pole here, then due to that pole this extra term would appear in the time response, and we have seen if we make P large, then the effect of that introduced pole would be negligible. So let us see in the pole zero map what we have discussed now. So here we are considering say 3 cases. So these all are the complex spring, that is sigma j omega, sigma j omega, and here we have two complex conjugate poles which are actually dominating poles, because we have already discussed what is dominating poles. Dominating poles are closer to that origin, because due to those poles the transient in the time response is accountable. That means the transient due to those poles, the effect of those poles in the time response is more compared to the effect of the other poles. That means if a pole lies far away from that origin, its effect would be less, because we have seen here just now, that means whenever that pole is placed far away from that origin, due to that pole the effect in the time response is negligible. The reason is the transient will be dying out very quickly. And here we have considered that two poles which are dominating poles and closer to that origin. But if we introduced a pole that is say at minus p, So this is a case, first case, and second case is suppose we have moved that pole little bit away from that origin. So this one is closer to that origin, this one is little bit further from that origin, far away from that origin, and here we assume that this pole is at minus infinity. So that means it is a standard second order system. And if we say that this is case 1, this is case 2, and this is case 3. So in that case, what would be that response? So suppose we take that G1. So G1 is transfer function. Here, suppose we consider that is 73, 626 divided by s plus 3 s square plus 4s plus 24 542. So suppose this is a transfer function, and here you can see whenever we have introduced that pole, then to make it normalize, so that is 24.543 into 3 equal to that we have discussed here to make this normalize. So this transfer function is represented in normalized form, and then we take another transfer function, that is that for G2 case we have shifted the transfer function, that pole towards left. That means that introduced pole is far away from the origin. So suppose it is at minus 10 s square plus 4s plus 24.542, and you can see that this particular part remains same because that is that standard second order transfer function, and we are interested into C. That means if we introduce a pole, what is the effect of that pole in the time response, and we are gradually moving that pole towards left. So this is at minus 3, this is at minus 10, and here we have shifted it to minus infinity. So it is just like a second order. This is a second order transfer function in normalized form. So suppose that G3 equal to 24.542 s square plus 4s plus 24.542. So here I hope it is now clear that suppose you have a transfer function, second order transfer function in normalized form, and if you introduce a pole, how to make it normalize, because just you multiply it with 10, so that steady state the response find steady state response would be 1. So now let us see what would be the time response. So if you plot those outputs getting from these three transfer functions, so what we get, so that is the t, and here you have that yt, and suppose this is that 1 applied input. So now the second order transfer function, so this one in under damped case we have seen how it looks like. So that is, suppose so this is a second order transfer function, and it is in under damped case. So this is that 3. This black one is 3. So now what would be the transfer response, step response for that 2? So if you plot it, you will see the plot looks like that. That is, it is very close to that 3. So this one is 2, and so this one is 1. So that means you can see here that these are the 3 transfer functions. So whenever there is no pole introduced to that transfer function, or we can say that that pole is placed at minus infinity, so then the black one is the time response, underdamped time response of that second order transfer function of that system. Then whenever that pole is placed far away from that origin, so then it has some effect on that response, but that response is very close to that second order response. But whenever that pole is moving towards that origin, then the effect of that pole on the response is dominating. Here you can see that whenever that pole is moving towards origin, that red one, so the response is remarkably different from that original response, black one. So from this particular discussion, what we have seen, whenever we introduce a pole to a second order system, so in that case, if the pole is moved away from that origin, that means in that case the dominating poles are the second order system's poles. So if the location of the newly introduced pole is far away from that origin, then we can assume that the response would be characterized by simply zeta and omega n, and its response would be very close to that original response, underdamped or overdamped, whatever it is. That means that response can be characterized by zeta and omega n. So now the other case, if we add 0 to this particular transfer function, then what happens? Adding 0, then how the response would be changing. So let us see. So here we can understand that suppose we have a transfer function here, that is suppose a transfer function gs equal to 1 by s square plus 1. Suppose we have a second order transfer function given in normalized form. So now if we introduce a 0, suppose we have introduced a 0 here, so then what happens? We can write this particular, so this is a 0 which is a stable 0, that means it is placed in the left half of that S plane. So now we can write that 1 by s square plus 0.5 s plus 1, and that is s by 1 by s square plus 0.5 s plus 1. So now that is output by input. So then this output ys equal to, so this transfer function s square plus 0.5 s plus 1 into us, and here you can see that 1 by s square plus 0.5 s plus 1 into us. So now if there is no 0, so that means if we have, suppose we have not introduced that 0, so in that case that response, that means that you would have for the second order system, the response, if you take the inverse Laplace transform of that, so the response would be this one. So if you take the inverse Laplace transform of this, so us equal to 1 by s, so then that would be yt. But here you can see that s into yt. Yt means if we take the inverse Laplace transform of that term, so then you would have yt here, but as s is there, so basically that would give dyt by dt. So that means if we say that the new response, that is y dash t, it would be equal to yt plus dyt by dt. So it is now interesting to see, once we introduce a 0 to the transfer function, so in this case it is a second order transfer function, so then that response would be y dash t is that original response yt plus dyt by dt. So if we take it as, so suppose that gs equal to that s plus a, that is s plus a divided by that s square plus twice zeta omega n s plus omega n square, and here we have omega n square, and to make normalize we need to multiply with 1 by a. So then what you would have, say we have that response, that is if we just take that is 1 by a here, so that means we have that yt plus this particular a into dyt, so that is a into yt. So here we can see that that one would be a into yt plus dyt by dt. Or we can just, if we just take only this particular thing, that means whenever we introduce a 0, that is s plus a into ys, so then what would be that response? That means if we just multiply with this one, so it is a s ys, that is that derivative, and a into ys, so if you take that Laplace transform, that is a yt. So we can see that the response that you would have, that is y dash t. So once you introduce 0 to that transfer function, so then the response that you would have, that is ayt plus dyt by dt. So this a is the 0. So now if a is very large, so then what happens? We can ignore this particular term whenever a is large, then it would be just like a scaled version of the original response. But if a is small, that means the 0 that you have placed, it is close to that origin, then it has significant effect in the output response. So from this particular analysis, what we have seen, we can write that if A is very large, if A is very large, if A is very large, we can neglect dy by dt. So here we can see we can neglect that one because A is very large. Dy dt effect, and it is a scaled version of the original response. It is the scale version of that original response. So if A is not, if A is not very large, then what happens? The response has an additional, component. Typically when t is very small, so in that case the dy by dt is positive. Typically dy by dt is positive. Dy dt positive because you can see whenever you apply an input to a system, so when just switch is on, that time response grows. So that means typically it is positive. Dy by dt is positive at the start, and hence it increases that overshoot. So that is important. So that means whenever you add a 0 to that transfer function, as dy by dt is typically positive at the time of start, so then it increases the overshoot. And interestingly, if you place that A on the right half of that S plane, that means A is negative, then you can see that you have that minus AYT, and that dy by dt that you would have, so that is actually has significant effect, and you can see the response initially it goes in reverse direction. That means you would have that negative kick. So when A is negative, that means the 0 that you have placed on the right half of that S plane. So this particular system is called that non-minimum phase system. We'll discuss in detail later non-minimum phase system. So whenever a system has 0 on the right half of that S plane, that system is called non-minimum phase system. We'll be discussing later in detail. When A is negative, a negative kick is observed. So a negative kick is observed means it is like that. So this is that time axis and this is that yt. And suppose you have applied one step input here. So whenever you have a 0 on the right half of that S-plane, so the response becomes like that. So that means here you can see that this is that undershoot. So that means whenever you observe this type of response, that means there is one undershoot. Here you can see there is one undershoot. So that means that system is a non-minimum phase system and it has a 0 on the right half of that S-plane. So we can just typically see what happens if we introduce 0, because we have just now seen that if you introduce 0, it basically increases that overshoot, and because of that dy by dt term, because of that extra term that appears in the time response expression. So here let us see typically what happens whenever we introduce a 0 to the second order system. So that is yt, and here suppose this is that standard second order systems whenever there is no 0, and then if you introduce a 0, suppose you have introduced a 0 at, I am just showing that qualitative response. So suppose that 0 is introduced at -5. Again, if that 0 is moved to -3, suppose that is at -3, so then you can see that whenever 0 is moving towards that origin, that overshoot is increased. So this is the typical response of a system whenever we add a 0 to that transfer function. So what we have discussed now, that means whenever we have a second order system, this is that typical transfer function given in normalized form, and if we add a pole, so the effect of that pole in the time response would be significant whenever that pole is closer to that origin, and whenever that pole is moved away from that origin, then that effect is less. That thing is also clear from here, because this particular term will be dying out very quickly. And what happens whenever we add a 0, and we have seen here, that means when we add a 0, then one extra term appears, that is that the derivative of that output, and as the derivative of output is typically positive when the system starts, so then it has some effect. But if a is very large, that means if the 0 of that introduced 0 is far away from that origin, so then we can neglect the dy by dt effect, and we can just see the output would be the scaled version of that original one. That means the typical nature like oscillation, overshoot, percentage of overshoot, etc. remain same, only it would be scaled up or down like that depending on the value of that a. But whenever a is small, that means that 0 is closer to that origin, then we can see that time response has, that means the effect of that 0 is significant in the time response of the second order system, and we can see whenever that 0 is moved to that origin, that overshoot is increased. and this is the case whenever I can write it here. This is actually non-minimum. This is non-minimum phase system's response. Whenever that 0 is placed on the right half of that S-plane, then in that case we observe a negative kick, that is called that undershoot, and this is that effect of 0 and that pole whenever we add to that normalized second order transfer function. So now we will start a topic what is called that steady state error, and we have discussed something in the beginning of this course, but now we will be discussing in detail. That means whenever you have a closed loop control system, and if you apply a command input, your objective is to get that output response exactly same as the command signal that you have applied. That is that. So now if there is a difference in between that observed output and the command signal, so that term is known as the steady state error. So that means when t tends to infinity or time is very large, the difference between that measured output and the applied command signal, the difference is known as that steady state error. So here we can write the steady state error. Steady state in abbreviated form I am writing SS. Steady state error is the difference between the input and the output for a prescribed test input. So prescribed test input means already we have discussed in control systems we use some standard signals like step input, ramp input, parabolic input, like that, as t tends to infinity. As t tends to infinity. So that means steady state error is the difference between the input and the input and output for a prescribed test input as t tends to infinity. So if we just draw the closed loop block diagram, so here we have a controller, that compensator, and then we have that plant. So if we close that loop, here we can see that once we close that loop, so this is negative, and here suppose we have given that reference comment and this is that output ys. So basically the error signal that we would get, we will get it here. So that is that error, and here suppose that reference command, that is that RT, that standard signal, and here you have that YT. So what is that steady state error? So steady state error that is limit t tends to infinity et. So that means if you take the difference between that RT, that is that reference command minus yt. So that is actually that steady state error. So what are the test signals? So test signals that we will be discussing today, that is that standard test signals, standard state test signals, that is that step input, ramp input, and parabolic. So this is 1, and ramp is that is t, and parabolic that is half t square. So here what we are going to study, so here whenever we have a closed loop control systems, then if we apply some standard signal like step input, ramp input, or parabolic input, then we'll be getting some output yt depending on what plant we have taken. So in that case, we'll be considering that controller equal to, say, suppose identity, or we can see that okay, controller and plant in combined form. If we take that this is that forward path transfer function, then for unity feedback case, what would be the output, that thing we can calculate, and then we'll be finding what is the difference between that reference signal and that output, that would be that steady state error. So this is actually ES, this is ES in Laplace domain, this is ES in time domain, this is ET. So this is actually that discussed now. So that is that steady state error, for unity feedback system. So that is important because it is unity feedback system. We will discuss later why it is important. The reason is, you can see here, whenever you have a closed loop control system, so suppose this is RS, and the forward path transfer function we take that is GS. So it comprises of that plant and that controller. Then if we take that unity feedback system, so then here minus and this is plus, then ES that you would have that error signal, is actually gives you that steady state error, because this ES, the steady state error as we have defined, that is actually minus YS, because RS is the Laplace transform of that reference command and YS is that measured output. So this difference is actually that error signal. And in case of unity feedback, you will get it here. But if it is not with unity feedback, that means if there is some transfer function here, then you can see that this is no longer error signal, because whenever you have a transfer function here, then this signal is different from that YS, and if you subtract it, it is not that error signal. So this is not that steady state error. So that is actually important. So first we will be considering the case whenever that feedback is unity. So then we can just write that RS minus YS equal to that GS into ES, and if we simplify it, we will get that ES, that steady state error signal, that is RS divided by 1 plus GS. So now we can find what would be the steady state error in time domain, because you can see it here that steady state error when time t tends to infinity et. And now what would be the steady error? We can get it just by applying the final value theorem. So applying the final value theorem, we can get that steady state error ESS, it is indicated by ESS, that is limit t tends to infinity et. So that means if you apply final value theorem here, so that is limit s tends to 0 s es. So now we get that es is this one, so that is limit s tends to 0 s. So in place of es I am writing that rs divided by 1 plus gs. So now let us see that in case of step input what happens. So if rs is step, then what happens? So that means if we apply step input, then what happens? So that steady state error, we get that limit s tends to 0 s rs by 1 plus gs. So whenever rs is step, that is 1 by s, so then this expression ess would be 1 by 1 plus limit s tends to 0 gs, because in place of rs if we put 1 by s unit step, so this ss will be cancelled out, this one will be cancelled out, so that is 1 by 1 plus gs, and if you just apply this limit you will get this expression. So then we are defining this particular term, as kp. So that means here we can write that 1 plus kp. So here kp is defined as limit s tends to 0 gs. So this particular term is called position constant. So this particular term is defined as position constant. So what we have seen, whenever we consider one unity feedback system, and if we apply rs as unit step, here you can see step input, then the steady state error becomes 1 by 1 plus kp, where kp is limit s tends to 0 into gs, and this is called that position constant. So now we'll see that whenever we apply that ramp input, then what happens? If we apply ramp input, then you can see that steady state error, because this expression already we have derived, this is that general expression with unity feedback control system, that steady state error equal to limit s tends to 0 s rs by 1 plus gs. So whenever you apply ramp, so that means that unit ramp, that would be 1 by s square. So then 1s and 1s will be cancelled out. So in the denominator 1s is there. So now if you apply limit, so the first term would be 0. So only you have that term, that is 1 by es is, that is 1 by. So let me just show this thing, that is s here, steady state error is s rs divided by 1 plus gs, and you have that limit s tends to 0. So now if it is ramp input, so limit s tends to 0, that is s 1 by s square, because it is unit ramp, then 1 plus gs. then you will get that s cancelled out, and if you take it here, so that is limit s tends to 0 1 by s plus sgs, and then it would be 1 plus limit s tends to 0 sgs. So like that step input, we define this particular term as kv. So then it would be equal to 1 by kv, and this kv is defined as that limit s tends to 0 sgs, and it has one name that is called velocity constant. So what we have seen, whenever we have that unit feedback system, then if we apply a ramp signal, ramp input, then that steady state error becomes 1 by kv. Kv is that velocity constant, and it is defined like this. Then what happens whenever we apply, say, parabolic input? So in the same way, that steady state error ESS equal to limit s tends to 0 SRS divided by 1 plus GS. For unity feedback system, we have that expression. And now that RS that you would have, that is 1 by S cube, because if you take that parabolic input, so that is S cube, then you can see that in place of RS, if you replace 1 by S cube, then you have limit S tends to 0 1 by, sorry, so here you have 1 by limit s tends to 0 s square gs, and this particular term is denoted as Ka. So Ka is limit s tends to 0 s square gs, and it has a name. It is called acceleration constant. It is called acceleration constant. So now what we have seen, that means whenever we have unity feedback system, then we can derive this relationship, that error signal equal to this one. And now if we apply the final value theorem, then we can find what is the steady state error. So we get this particular expression. Then if we apply different standard input signal, step input, we find that the steady state error would be 1 by 1 plus kp, and where kp is that position constant, and it is defined like this. And whenever we apply ramp input, then we get that steady state error equal to 1 by kv, where kv is the velocity constant. And in case of parabolic input, it would be 1 by ka, where ka is the acceleration constant. So we call these three constants as, we call these constants as static error constants. Static error constants. That is that position constant, velocity constant, and acceleration constant. So now there is an important definition. That means in this case, if you look at the unity state feedback system, we'll define that how many poles are at origin. So that means the number of poles at origin is known as the type of a system. So that means, suppose if you have a transfer function of gs, that is 1 by s into s plus 1. So in this case, you can see that at origin there is one pole. So this particular transfer function is called type 1 system. So let us see the number of, so this is very important, the number of pure integrator. So pure integrator means it will introduce 1 by s. So number of pure integrators in the transfer function is known as the type of system. So the number of pure integrators in the transfer function is known as type of system. So this is very important. For example, so here you see that no integrator. So no integrator. So suppose you have a transfer function that is gs equal to 1 by s plus 1. So there is no integrator, no is pole at origin. So here this particular transfer function is called type 0 transfer function. So now suppose one integrator. That means you have a transfer function that is 1 by s into s plus 1. So you can see that there is one integrator that is 1 by s. So here this system is called type 1 because the number of pure integrators in the transfer function. So here in this transfer function one integrator is there, one pole is at origin. So that's why this transfer function is called type 1 transfer function. So now two integrators. So suppose you have a transfer function which is 1 by s square plus s plus 1 plus s plus 2. So here you can see that there are two integrators at origin. So that's why it is called type 2 transfer function and so on. So that means whenever a transfer function is given to you and just by looking at the transfer function, how many poles are at origin or how many pure integrators are present in that transfer function, that is actually the type of a system. So whenever it is type 0 system, that means there is no integrator, and whenever it is a type 1 system, there is one integrator. So this is like that. So now let us see one important and interesting thing, that this type of a system is actually would decide what would be the steady state error. It has a direct relationship with steady state error. We have seen now that we have defined three constants. One is that Kp and Kv and Ka. So what is Kp? We get that Kp position constant, that is limit s tends to 0 gs. We can see it here that Kp, and Kv is sgs and Ka is a square gs. So Kv is limit s tends to 0, that is sgs, and this one is Ka. Ka is limit s tends to 0 s square gs. So we have defined three constants, and we found that this Kp is defined whenever that signal is step signal and that steady state error is 1 plus Kp, that is 1 plus Kp. We have seen it. The steady state error is 1 plus Kp here, and in case of velocity and error constant, it is directly 1 by Kv and Ka. and here it is steady state error is 1 by kV, and this is steady state error, that is 1 by Ka. So now we can make a table like, so what input we have. So suppose input is step, then ramp, and then parabolic. Then steady state error. So steady state error we have seen, that is 1 plus Kp, and here ramp is 1 plus Kv, and here that is 1 plus Ka. Then if we have type 0 system, so type 0 system means there is no integrator at the transfer function, or there is no pole at origin. So then what is that constant? That is static constant. So static constant means that is that position, velocity and acceleration constants, and steady state error. So static constant in case of step signal, and whenever type 0, so type 0 means in the GS there is no, so type 0 means here if you look at here that this is a type 0 transfer function, and if you take S limit, so what is Kp? So Kp you can see here, that is limit S tends to 0 GS. So if you have a GS like this, that means this Kp would be in this case 1, or if you have say GS equal to suppose 1 by S plus 2, so then limit S tends to 0 GS, that one would be equal to half. So that means this is that Kp. So Kp would be finite whenever that system is a type 0 system. So this is actually a finite value, so that means static constant is equal to, this is a constant value, finite constant, and the steady state error that you would have, that is 1 plus Kp. Now what would be Kv? Kv you can see that this is that expression, and GS is say suppose 1 by S plus 1, because we are discussing type 0 system. So whenever 1 by S, so in this case, this is that case whenever what would be Kv? So Kv would be equal to that S divided by S plus 1, because GS equal to S plus 1. Now if you just apply limit S tends to 0, so as in the numerator S is there, so then Kv would be equal to 0. So you can see here that Kv is equal to 0, and similarly as it is S square into GS, so then that constant would be equal to 0. And you can see what is the error, steady state error in case of ramp input, that is 1 by Kv. So 1 by Kv means 1 by 0, so that means that would be, that is infinity, and here this is infinity. So that means you understand that whenever you have a unity feedback system, then if you apply say step input and your system is a type 0 system, the transfer function that you have taken, it does not have any pole at origin, then you have some steady state error in case of step input, but in case of ramp and parabolic, that steady state error will be infinite. And then if you take type 1 system, so then what happens? So the static constants that you would have, static constants, and here you have that steady state error and static constant. You can see whenever type 1 system, so type 1 system means, so suppose GS equal to 1 by S into S plus 1, that is type 1 system. So now limit S tends to 0 GS, that is that Kp. So then we can see here that limit S tends to 0 1 by S plus S into S plus 1, so that one equal to infinite. So you can see here that static constant becomes infinite. Then what would be? So kv equal to limit s tends to 0 sgs. So if it is sgs, then it is a type 1 system. That means one pole at origin. So then that is s tends to 0 s by 1 by s plus 1. You can see that this s and s will be cancelled out, and that would be equal to 1. So that means this is a finite value. It is a finite value. And whenever you calculate that Ka, that is that static acceleration constant, that is limit s tends to 0 s square gs. So now you can see that limit s tends to 0 s square 1 by s plus 1, and here 1 s will be cancelled out, that is s by s plus 1, and as in the numerator 1 s is there, so that would be equal to 0. So that means in case of type 1 system, so once you change the type of that system, if you introduce one integrator at origin, one pole at origin, then you can see how the static constant is varying. So static constant in this case, step response, it is infinity. And just now we have seen that kv, velocity constant, would be the constant. It is some finite value, and ka you will get, it is equal to 0. So now what is the steady state error? Because in case of step input, that steady state error formula is 1 by 1 plus kp. So then 1 by infinity means it is 0. That means one interesting thing you can see here, whenever you have one unit step feedback system, and if this plant is a type 1 plant, that means it has one pole at origin. If you apply step input here, the output also will track that reference command, means its error signal would be equal to 0. Here you can see that steady state error is equal to 0. So that's why whenever we want to track a reference command, and reference command is step input, then that system at least should be the type 1 system. That means at least it has one pole at origin. And here you can see that what is that steady state error in case of ramp input, whenever the system is type 1 system, that is 1 by kv. So because kv is constant, so it has some finite value. That means if you give ramp input, you cannot have that 0 steady state error. And as that ka is 0, so 1 by 0 means it is infinite. Steady state error would be there in case of parabolic input. Now if we go for type 2 system, so then what is that constant? Static constant, and here you have that steady state error. So static constant, this is the type 2 system. So type 2 system means, suppose you have that gs equal to 1 by s square plus s plus 1. So this is type 1, and this is type 2. This is type 2 because you can see here that two poles are at origin. So now what will you get? That is kp equal to limit s tends to 0, that gs. So then you can see that limit s tends to 0, 1 by s square plus s plus 1. So whenever in the denominator there is a pole, that means it would be equal to infinite. And what is kv? That is limit s tends to 0 sgs. So that means limit s tends to 0, that s square plus 1, and here you have one pole at origin, so you can see that that would be infinity. And in this case ka, what is that? That would be limit s tends to 0 s square into gs, and limit s tends to 0, and here s square Now the bottom you have again s square and s plus 1, so this one will be cancelled out, and here you can see that s equal to 0, so this is equal to 1. That means it is a finite value. So interestingly, you can see that the static error constant, whenever you have that type 2 system, then Kp is infinite, Kp is coming infinite, and when Kp is coming infinite, you can see that steady state error is coming 0, and Kv is coming infinite. Here you can see whenever it is infinite, then it is coming 0, and whenever Ka is constant, then you have the steady state error, that is 1 by k. So from this table, what we have seen, that means when we consider a unity state feedback system, and if we apply various types of standard signals like step input, ramp input, parabolic input like this, then we can find what is the static error constants, and that static error constants we have already defined, and it depends on the what is the type of that system. So type of that system is defined as how many poles are at origin, or how many pure integrators are involved in the transfer function. And then we can see that if we apply a step input here, so to get steady state error equal to 0, at least we should have one pole at origin. At least it should be a type 1 system. That means the system's type, if it is 1 or above, so in that case, if we apply step input, the steady state error would be equal to 0. But if it is type 0 system, so always you would have some steady state error. So it is very important and interesting result. So let us see one example. Say, so one example. So suppose you have one closed loop system. Suppose you have a closed loop system that is 500, s plus 2, s plus 5, s plus 8, s plus 10, and s plus 12. Now, if you apply one reference command here, then what would be the steady state error in this case? So this is that negative feedback, and here you would have that steady state error, and then you can see that there is no integrator here, so this is type 0 system. And whenever it is type 0 system, you can see that Kp would be finite, and if you just put limit s tends to 0 gs, you would get that value, that is 125 by 24, so then that would be 5.208, and Kv value, if you calculate, that is 0, and Ka, that you would have, this is 0. So you can also see it from this particular table. So that is type 0 system, Kp is constant, and Kv and Ka, you will get 0. So from here you can see that what would be the steady state error. So that steady state error, ESS, for step input, that is equal to 1 by 1 plus Kp. Kp is 5.208. So this value you will get 0.161. So that means whenever you apply a step input, here, unit step input, so this is 1. So you can see that the final response, so because here you need not know exactly what would be the transient, I am just going you the steady state. So as error signal, as et equal to, that is RT minus YT, when t tends to infinity, that means at steady state. So here limit t tends to infinity. So reference comment is 1, and YT we do not know, and as that steady state error equal to 0.161, that means it is positive, so that steady state error it would be 1 minus 0.161. So this is that output you would have. So this difference, it is 0.161. So now one interesting comment, that means, or example you may say, that this is that example, that is whenever what information is contained in the specification Kp equal to 1000. So that means, suppose a problem is given where it is said that Kp equal to 1000. So from this particular specification, what information you can have? What we have seen, that Kp means it is a position constant, and position constant is defined associated with the step input. And of course, whenever we are defining those constants, we assume that the system is stable. So the first information that you would have, that is that system stable. So those constants are only valid associated with the stable system. And second thing is, Kp is finite. Kp value is finite. So here you can see that Kp value is finite. It is 0, it is infinity and infinity in other systems, but it is finite whenever it is type 0 system. As this Kp equal to 1000 here, that means from this particular specification, it is clear that the system is a type 0 system. And what is the test signal? The test signal is that step input, because this Kp is associated with that step signal. And then what is that steady state error? Steady state error equal to 1 by 1 plus Kp, means 1 by 1001. So that means in a particular problem, if it is said that the position constant, that Kp equal to 1000, it implies that the system is stable. The system is stable because all those constants are actually defined for stable systems. It is a type 0 systems because it is a constant. The input that you will be applying, that is that step input, and steady state error equal to this. So from this particular information, we can have those 4 informations. So now this is that last one, that is what happens. So far we have discussed, that means steady state error with unity feedback. Now what happens if it is non-unity feedback? Steady state error for non-unity feedback. So let us draw that block diagram, then it would be clear. So now you see the scenario is like this. Whenever we have a plant here, and so far we have discussed it is unity feedback, but now you have a transfer function in feedback. So now here you have that ys, and here you have applied that reference command. Then this particular signal is not that error signal. The reason is, error signal means, here you can see that error is basically rs minus ys. This is that error signal, but here you can see that this is not error signal. So what we can do? So we will be transforming this particular loop as follows. So this is that rs, and now we have that gs here, we have hs as it is, Now we'll be adding one loop with negative 1, and again, so here minus, so minus minus plus, then here you have that minus. So that means what happens? In this case, you can see this is minus minus plus, so we are adding plus 1 and again subtracting minus 1. So basically the same thing would remain, so that is that minus. So original loop you will get. So now we can see that if we combine these two, this one and that one, that is would be hs minus 1. So we can draw this particular block diagram, that is that rs here. So this is that rs, and if we combine these two, so then we have that gs, and that is hs minus 1, and we have another loop, that is this one. This is that negative. So now we can see that this one and that one, there with that feedback, so easily we can simplify it. That means we have that rs here, and if we combine this one and that one, that is gs, we have that gs by, as it is negative feedback, that is 1 plus gs into this feedback, so that is gs hs minus gs, and the rest of the feedback path is this one. So then now this is ys, and now you can see that this one is coming es. So what we have seen, that means whenever we have a feedback path like that, es, gs and hs, this is no longer an error signal. So we have transformed this particular path. That means we have added one minus 1 and plus 1 with negative feedback, and then we have combined these two, we'll get this one. Then we can transform it in that way. So then what happens? This particular transformed loop, closed loop, is with unity feedback, and then we can apply the steady state error formula that we have done. So if we say that this is that ps, this is ps, so now we can see that ps equal to gs divided by 1 plus gs hs minus gs. So that means whenever you have a non-unity feedback system, so then applying this transformation, you will get one unity feedback system with a new transfer function, that is that ps. So now you apply all the constants and all the concepts that we have discussed today on the ps, not on gs, because if you apply all the formulas on gs, it would be wrong, because this is not error signal. But after transformation, you can see that the transform plant is ps, and now this is es. So to find the steady state error, you need to apply all the formulas and finding all the constants for ps. So today what we have discussed in this lecture, we have discussed that what happens if we add a pole and 0 to that normalized transfer function, how that response differs with that original one. The second, we have defined what is steady state error, and we have started discussing on that unity feedback system, and we have defined three constants. One is position constant, velocity constant, and that acceleration constant, and we have calculated steady state errors for different signals and considering different type of system. And finally, we have discussed, that means if the feedback is not non-unity, then how to transform it into unity feedback system. So in that case, the transform plant is that PS. So we need to find all the constants considering that forward path transfer function as PS. Thank you.